In this video, I'm going to be reviewing some basic descriptive statistics. So if you've taken any sort of basic statistics class or really any sort of basic math class, you may have encountered some of these calculations before. However, I bet you at least one of them is new. I'm also going to be covering how to do some of these calculations in Excel. So even if you are familiar with most of these calculations and most of these statistics, you still may find value in this video if you want to learn how to do these various statistical calculations in Excel. I'm going to start with a very basic introduction as to what descriptive statistics is and statistics in general. So before we do that, we need to understand some terms in statistics. First, we need to know what the population is. So population is all elements of a set in data. So this might be all of the Floridians, so all the people who live in Florida, and this is usually represented by a large capital N. However, when you're doing studies, you can't usually grab all of the elements of a set of data. You have to take a subset of that actual population. You're going to analyze that subset. So we call that subset the sample. So that is the smaller group that we take from the population to analyze and to collect data on and do statistics on. It is very important that the sample represents the population. And if you want to learn more about that, you can watch the video on sampling methods. A sample is usually denoted by the lowercase n to show that it is a sample and not the population. Now, parameter is a property or characteristic of the population. A statistic is a property or characteristic of the sample. So ideally, parameters should be approximated by the statistic. So statistic should match what the parameter is. That means that we're doing a good job and we're doing good science. Now, statistics is a way to analyze data, very useful, used across a wide variety of fields. Descriptive statistics are basically numbers or calculations that summarize and describe data. So descriptive statistics means that we're going to come up with some numbers that help us describe a data set. Today we're going to be really looking into summary statistics, or just the basic summary methods. Moving forward, if you go on to more advanced statistics, you may start to learn about inferential statistics. These are techniques and methods that allow you to make generalizations or infer findings about a population from a sample. So for example, you might be able to say whether two populations are extremely similar or extremely different. You can't necessarily do that off of descriptive statistics because you are just inserting your opinion at that point, since all descriptive statistics does is describe and summarize data. If you want to have some hard findings, you need to use inferential statistics. But descriptive statistics are very useful, as they usually give scientists or economists or psychologists or other people who work with large data sets a first way of looking at the data and kind of wrapping their head around it. The first type of summary statistic we're going to be looking at today are measurements of central tendency. So central tendency just basically means if we look at the data in general, is there a value that seems to represent the data the most? And there are three measurements of central tendency that are pretty common that scientists and other people use to get an idea of what is that number, that value that represents the data. And usually we call this central tendency because it's usually somewhere near the middle of the data. The first central tendency term we're going to look at is the average. This is also often called the mean. And this is calculated by adding up all the data points or all of the values and dividing it by the number of values that there are. Mathematically, average is usually denoted by a lowercase letter. Like here we have X with a little line above the top. So that's a shorthand way to say, hey, this is the average or the mean of that set. This also goes along well with vector notation, since lowercase letters usually are indicative of a vector, which I've talked about in another video. So it's an easy to say, hey, this is the average of that vector, this is the average of that set of data. Excel has a nice handy little formula for us that we can use to actually calculate the average, and that's just equal average, and then you highlight the data that you would like to calculate that for. So I'm going to actually jump into Excel to show us how to do this. So here we can see that I have a set of data. This is a study about bean plants. So we have IDs for each bean plant, so we know which bean plant each set of data corresponds to. And then each bean plant also has an associated height in inches. So first, as with everything in Excel, we want to make sure that we have a nice label so that we know what we're looking at. So I'm going to put in mean in this box, or in this cell, and then next to it we're going to type equals average. So you notice as I start to type in Excel, it comes up with a lot of suggestions. Oh, do you mean this? Oh, do you mean that? I would highly, highly, highly recommend you do not ever click on these suggestions. A lot of times you will accidentally click on the wrong one, and then your data won't make any sense, or you'll be getting a statistic that's meaningless because you think it means something else. Go ahead and just always type the formulas in yourself. So I'm going to finish with average, and then I'm going to highlight my data here, close the bracket, and hit enter. And now I have the mean or the average of my data. Let's go back to the PowerPoint. Next, we're going to be looking at the median. So mathematically, this means if you took all the values in a data set and you lined them from the smallest value to the largest value, and you went and you picked the middle value, that is the median. Again, Excel has a nice little formula for us to use. Now you may say to yourself, well, this sounds pretty simple. Why would I want to do this in Excel? Well, if you have a set of 20 data points, maybe it doesn't take very long for you to align all those data points in order and then to pick out the middle value. But if you're working with hundreds or thousands of data points, as environmental scientists often are, or other types of scientists, or if you're a data scientist, hundreds of thousands of data points, it's much faster to use a formula like this. So let's go into Excel. We're going to put in the label for the median. This is going to be equal median. Again, it's giving me that suggestion. I'm going to get into a good habit of ignoring it. Highlight my data and hit enter. You can see that they're actually pretty similar for this data set. That is true of a lot of different types of data sets. All right, the last measure of central tendency we're going to talk about is the mode. So mathematically, this is what value occurs most often in a data set. So again, this might be actually pretty easy to see if the data set is small and you see, hey, the number 5 occurs a lot of times, or the number 6 occurs a lot of times. But when you're working with large sets of data in the real world, it's much easier a lot of times to use a formula, take advantage of these software systems. So the Excel formula is just equals mode. We're going to go in, put in our label, equals mode. Again, I'm going to ignore all these suggestions. And the mode is 5. So the mean, median, and mode are all pretty similar in this set of data, which is pretty typically the case. Next, I want to talk about some other summary statistics other than just the central tendencies. Those may be a first starting point, but often there are more we want to know about the data other than just what is that middle value, what is that representative value. So the next thing we're going to talk about is the measure of spread. So measures of spread gives an idea of how far the data set is distributed away from that central tendency. So are all the data points pretty similar, or do they go over very long, or can they be very different from each other? This gives us that idea. There are a few ways that we might want to figure that out. The first is the maximum value. Mathematically, this is just picking out, determining what is the largest value in that set of data. Excel has, again, a nice little formula for us, which is pretty intuitive. It's equal max. So going back into Excel, we're going to pick out our maximum value. And there we go. We can see our maximum value it calculated us is 9. And this is a pretty small data set, so we can also see here that the maximum value in the data set is also 9. It's all the way there at the bottom. Bean plant P. Another measure of spread that's kind of the opposite of maximum would be the minimum values. Mathematically, this is just the smallest value in a set of data. And again, Excel has a nice handy little formula for us, which is equal min. Go back into Excel. Type in our formula. Select our data and hit enter. Great. So again, we can see that the minimum value is 2. That's also pretty easy to see just looking at the data set. That appears to be the second from last value, being plant O. It's only 2 inches in height. It's just a little guy. Next, we are going to talk about the range. So the range gives us an idea of the total spread of the data. So what's that distance between the maximum and the minimum values? So mathematically, to calculate the range, you would take the maximum value and minus the minimum value from it. Excel does not have a built-in formula for range. You have to do it yourself. But that is not so difficult because we can take advantage of the formulas for maximum and minimum value to create a new formula. So you see here, we're just going to put equals max minus min. In this case, you would highlight in those parentheses the same sets of data. However, since I already have the maximum and the minimum calculated, I can take advantage of those. So I'm going to put in equals, and I will highlight the cell where the maximum value is, and then minus the cell where the minimum value is, and I can hit enter. And that will give us the same value as if we had done it this way, which is equal max, highlight my data, minus min, and then highlight the same set of data. You can see that the value is the same, it's still 7. So this is something you might want to get into your habit of with Excel, is trying to take advantage of those formulas you have already built, because it does take less effort to just put in equals and then select other cells sometimes than putting the entire formula in again. Okay, so one more measure of spread that I want to talk about, and this is a quartile. So a quartile, as the name infers, is what happens when we divide a data set after we've lined it up from the smallest to the largest value into 4 quarters. So if you look at this image I've placed here, you can see that there's the first quartile, and there's 2 data points to the left of that. To the right of it, there's 2, so that's between the first and the second quartile. And then there's 2 data points between the second and the third quartile. And then there's 2 data points beyond the third quartile. There's 2 eighths. So we've just basically here said, okay, what data points are we going to select if we are going to divide the set of data into quarters, essentially. You can also think of this as in terms of percentile. So the first quartile is also often referred to as the 25th percentile. This means that 25% of the data is below that data point. The middle quartile is equivalent to the median. It's also often referred to as the 50th percentile because half of the data should be represented below that point. And the upper quartile, the third quartile, is often referred to as the 75th percentile because 75% of the data should be below that point or less than that point. Right? In Excel has a more complicated formula for quartiles, which lets you determine which quartile you actually want to see. So in Excel, we would put an equals quartile, and then we would, where A is in this formula, we'd select the data, and then put comma, and then we put in either a 0, 1, 2, 3, or 4, where 0 is the same as the minimum value, 1 would say give me the first quartile, 2 would give you the second quartile, and 3 would give you the third quartile. And then lastly, 4th would give you the maximum value. Now for our set of data, we've already determined the minimum and maximum value, so we don't need to do the 0 and the 4 to get those values here. So we're just going to go in and we're going to determine what the first, second, and third quartiles are. So let's go into Excel, and I'm going to do all my labels first. All right, so let's go in and put in those formulas. This is going to be equal, quartile. Again, it's trying to give me suggestions. We're going to ignore that. And then we're going to select our data. And then comma, since we want the first quartile, we put in the number 1. Close the parentheses and hit equals. Great. Now we're going to do that again. Select our data. We want the second quartile now, so we're going to do comma 2, close parentheses. And then one more time. And then comma 3. All right, so now we've got our first, second, and third quartiles, which give us a little bit more idea of that spread of the data. All right. The last other summary statistic you may find very useful is the sample size, which basically tells you how many values are in that sample or how many data points are there. This can come in handy in more advanced calculations where you need to integrate that into the formula. We haven't needed that so far today, but you may find that handy in other situations when you're calculating statistics. And mathematically, you would just count the number of values in a sample. Of course, if it's a very large data set, a lot of times it's easier to ask the software system to do that for you and faster. And in Excel, you can do that by equals count. So here, I'm going to put in the lowercase letter n. Oh, keep it autocorrecting for me. Well, I'll do sample size. So it won't let me do the n. And then we're going to equals count. And enter. So we can see that there are 16 data points in this sample. All right, the last major descriptive statistics we're going to talk about today is the weighted average, which maybe you have encountered before, maybe not. It is important, especially with environmental data, where there may be other factors that influence your sampling design. It would be pretty easy if you are in a lab and you want to do an experiment on, say, rats, to ensure that all the rats are the same age or all the rats are the same size. You just go pick them up from wherever they get rats from. If you're in the environment studying rats, though, you may get a bunch of rats that are actually a wide variety of sizes when you pick them up. A weighted average can help you account for these differences in your sampling design. So a weighted average is a kind of average or kind of mean, where instead of each data point contributing equally to the final mean, some data points contribute more than others. So they have some sort of influence that makes them matter more than others. If you're looking for the average amount of some contaminant, like in those rats, a larger rat might contribute more contamination because it's just larger and it's been around more than a smaller rat. So you might need some way to account for that. We have this really scary formula over here on the left, which actually should not be that afraid of. If you look at the top where it says xi times yi, all that means is you're going to multiply your value that you would normally take for an average times its associated weight. So what does that weight mean? Well, let's look at this table here over on the right. So here we have some data from the Florida Keys. We have different reefs in the Florida Keys and counts of lobsters that have been observed on those different reefs. So we see that an Alligator Reef had 70 lobsters, and Pickles Reef had 100. Turtle Reef only had 1. Widespread of data here. Why might that be? Well, if you look at the next column, the reef area in acres, you can see that these reefs are actually pretty different sizes. And no surprise, the reefs that are larger tend to have more lobsters than reefs that are smaller. So for example, Pickles Reef has 100 lobsters and it's 31 acres versus Turtle Reef, which only has 1 lobster and is only 4 acres. So just taking a simple average or simple mean of these lobsters is not going to really give you an idea or an accurate way of thinking about how many lobsters there are per reef, because all the reefs are different sizes. This is where that weighted average comes in. So looking back at this formula, the xi, that just means taking the number of lobsters on each reef and multiplying it times its weight, which in this case is the reef area. So you would multiply the lobsters per reef times the reef area, add up all of those values, and then divide it by the sum or the total value of all the reef areas added together. Let's walk through this in Excel since it probably will be a little bit easier to see visually. So you can see in my Excel workbook, I have down here at the bottom this first page labeled, this first sheet as summary stats, so I know that this is my summary statistics page, and then next I'm going to go to my weighted average page. So again, good practice is to always label your sheets so you can see what sheet you want instantly and click on it. I've already imported this information or this data about the Florida Keys lobster population into Excel, as you can see here. And I'm just going to walk through how to do this calculation for this weighted average. And the first thing I want to do is create some labels, right? So I know what my calculations are. If I close this workbook in a month, or if I close this workbook today, and I went back in 2 months or 6 months, I want to be able to see what all these different formulas are without having to guess. So what's that first calculation we need? Well, we need to multiply all the x's, so all the numbers of lobsters per reef, times all the weights, which is the reef area. So I'm going to put a label here, which is xi star y. So this is going to be my weights. And for that, I'm just going to do equals the number of lobsters times the weight, which is the reef area, and hit enter. And I'm going to do that for the other one, so I'm just going to copy this formula and paste it down. Great. Now I need to calculate my next statistic, which is the total weight. Looking here on the bottom, I need the total weight of the reef areas, so adding up all the reef areas together. So I'm going to put my label here. So it's going to be my sum of yi. I'll put a little colon there to show that it's next to it. And here I'm going to add up all the reef areas. I'm using this built-in Excel function, which is sum, which just adds up all the values in whatever data you select. There. So there's all my areas added together. Actually, I'm going to change this so it's just sum because that will make it easier for my next step. And then let's go back here. The next thing I do, looking back at the top of that formula, it's xi times y. I got to add all of those up. That's what this weird E-looking symbol means. It means add all of those up. So this formula sums all of the reef areas. Now I want to have the sum of all of these areas. So again, taking advantage of Excel, I'm going to just copy this formula, move it over here, and paste it down. And that's just going to sum all of the values above it. If you'd like to know more about how to use this built-in copying and pasting to your advantage, I highly suggest that you watch the video on matrix notation in Excel. All right, now I need the last step of my weighted average. This is going to be the final number, which is to divide the top by the bottom. All right, so I'm going to do a label here. Give me a little label first, and then that is going to be equals to the top, and then slash, that's going to be divide by the bottom, and hit enter. So my average numbers of lobsters per reef, as per my weighted average, is 193. So this is very different than if we had, let's just for fun, take the average of the lobsters, which is only 100, really. So this doesn't, this number does not account for all those differences in the reef area. So this is why the weighted average can be really important. We can see that actually one reef is probably influencing this number a lot more than others, and that's the Elbow, which has 300 lobsters on its reef and is much, much larger than the other reefs. So in summary, descriptive statistics can give an idea of the spread size or typical value of a set of data. Excel has many formulas built in that can calculate these descriptive statistics for you. Those include the mean, median, and mode, which are all measures of central tendency, the minimum and maximum, and quartiles, which are all measures of the spread of the data, or your sample size, so how big your data is. However, some other statistics need to be calculated by using a combination of built-in formulas. And we saw this with range. We can actually use the built-in minimum and maximum formulas to calculate it. Or the weighted mean. We can use a variety of Excel formulas to calculate it. However, descriptive statistics is not as robust as inferential statistics. Descriptive statistics, again, are just going to describe and summarize the data for you. If you really want to be able to say a finding, such as this thing causes that thing, or these two populations are very distinct and different, you need to move on and use inferential statistics.